This video is going to cover topics like open and closed sets and that kind of thing, but in the context of a normed vector space. And the starting point for all of this stuff is the balls. So open balls and closed balls and that kind of thing. And the textbook has a nice picture for us here in R2. R2 is the ordinary plane, and they have different balls depending on which norm you're working in. So here is what you would normally think of as the unit ball in the plane. It's a circle. Here is a diamond, and that is actually also a unit ball, but in a different norm. And this one in particular is the one norm. So this is if you measure the norm of the vector xy as the absolute value of x plus the absolute value of y, then the set of points where the absolute value of x plus the absolute value of y is a less than or equal to 1 is exactly this diamond shape. So that is a perfectly good unit ball. We're going to see the definition in a second. Actually, you can peek ahead and take a look down here. And it is just a different shape. I did notice that the textbook is actually mislabeled here. So that this one, the ordinary one, is the 2 norm. So this should say xy 2 is less than or equal to 1. That's the ordinary Euclidean norm. So that's wrong. And then this one is the 1 norm. And this one is the infinity norm. So this one is the norm of xy is the maximum of x and y. The maximum of absolute value of x and absolute value of y. So whichever is bigger, x or y. Okay, so I guess the person making the textbook was like, oh, first one, second one, third one, 1, 2, 3. But they are not 1, 2, 3. They are the 2 norm, that's ordinary circle. The 1 norm is a diamond, and the infinity norm is a box. And what is the actual picture being drawn here? It's the set of points where when you measure them in that norm, they are less than or equal to, depending if you're doing open or closed, some radius r. So these are the open ball, that's if you do less than r. The closed ball is if you do less than or equal to r. And the sphere is the sort of like edge where it's exactly equal to r. And once again, I think you should think of this as distances. In an ordinary metric space, you would say the ball of xr is the set of points y in the space such that the distance from x to y is less than r. And that's exactly what we're doing here. We're just measuring distance using the norm. So the distance function is replaced by the norm of the difference between the 2 points you want to do. That's exactly a perfectly good distance function, but it also respects, translation and stuff like that. So it's like a special type of distance function. It's a special metric space. And we have all the usual things, open, closed, and sphere, and so on. And if you have these open sets, you can think of this as a topology, which is a fancy word that just means think of all the open sets. If you say all the open balls, those are the building blocks of my open sets, and you define open sets like this. Okay, here are some pictures. Okay, and again, with the typos, look at this. Amazing. Okay, this should be the 1 norm, this should be the 2 norm, and this should be the infinity norm. Okay, and here is the first great example in the kind of thing we want to actually look at in this course. Is we don't want to look at points in R2. We want to look at function spaces of functions. And our favorite space of functions is the space of continuous functions. So as a reminder, C of AB is the set of continuous functions with domain AB, continuous functions f from AB to R. And we have a bunch of norms on it. One of them, the most common one, is the max norm, the maximum value taken in some interval. And then if you have this max norm, you can draw a ball around a point. What does it look like? There's a picture in the textbook. Here it is. So this is the ball centered at the function sine of t. F of t equals sine of t is the function in the middle here, like this. And the ball of radius 1 around this means you can go 1 higher. So this the sort of distance is 1, and 1 lower. And this any function that fully fits in this envelope will have a max norm between the sine function and that being less than 1. So this is really the inequality the function g of t must satisfy to be in this ball. G of t is in the ball around sine of t, comma 1, if and only if the maximum difference between g of t and sine of t is less than 1. So the maximum over all possible t's has to be less than 1, and that means the furthest away it ever gets is distance 1 away from the original function. So for example, here is some weirdo function that is in this space. That is a totally valid function that is in there. It's a continuous function, and it is maximally distance from f of t equals sine t is less than 1. So any possible function like that. So it kind of feels kind of similar to what you do in R2, like what our starting example. The textbook does have a nice little warning here, which is don't be mixed up. It is not the set of all points of the shaded area. So don't think that we're talking about points in R2, we're talking about functions. The points are functions. So really, this is, you can think of this as like, if you want to think about this, some people call this the sociological way of thinking about functions. The space of all possible functions is some kind of area like this. And then here is the function, sine of t, right? Some particular function, some point in the space. And we're talking about all the functions that are within distance 1, right? And you can draw kind of like a blob just to like help yourself think about it like you think about things in R2, but it's not things in R2. Every single point here is its own function. So, every single point here is its own function. There are infinitely many functions that are within distance 1, and we're going to see that actually in some sense, the infinitely many functions that are within distance 1 here is kind of really, really big. There's so many functions that are within distance 1, and it's kind of in some sense bigger than it is in R2, where you have just a circle of points. So this is kind of like the cartoon picture over here that I drew of what's going on and how it relates to what's going on. And then this picture is another way to imagine the same thing. Okay, if we have these open balls of things of different radiuses, we can talk about open and closed sets, and that is the next thing. Open and closed sets. A subset is called open if for every x in S there exists an epsilon greater than 0, such that the ball centered at x of radius epsilon is entirely contained in S. And so what this means is I kind of think of them as having fuzzy borders. This is how I think about open sets. And what it means is if you pick a point in the open set, even if you're really, really close to the edge, there's always a little bit of room where you can sneak a ball in. The opposite of that would be something like a hard edge, right? So if you have a set of points with a hard edge, if you pick a point right on the edge, there is no amount of room that you can put around this that will be entirely within the set. So that's an open set. The opposite of an open set is a closed set, but it's really important what you mean by opposite. Opposite here means with respect to complements. So open and closed are opposite. They are opposite with respect to complements. And so that is what is written here. It is called closed if and only if its complement is open. So E is closed if and only if. Everything except for I wrote E, but I meant to write S. Let's fix that. S is closed if and only if E take away S, which is also called S complement, is open. So open and closed are opposites with respect to complements. It's very important that you know they are not logically complements. If something is open, that does not mean that it is not closed. You can have sets that are both not open and not closed. And a good example of that would be something like this. If you have a fuzzy wall on one side, kind of for points over here, you can always sneak a thing in, but for these points, you can't. And so this set is not open and not closed, not open and not closed. Okay, you might know this stuff very well from your previous analysis class, and that is great. So open means you can fit a little ball around every single point. Closed means the complement is open. And indeed, in this little square that I've drawn over here, the complement is open because you can, for any point, you can always fit a little ball no matter where you pick a point. All right, that's open and closed. The definition, all sorts of nice things are true about them, with respect to unions and intersections. The proofs are left as an exercise. They are not so complicated. Of course, if you can fit a ball around the outside, then you do a union, then you can still fit a ball around it. Okay, very easy stuff. This one, I think, is the most important thing to know about closed sets. So why is it called closed at all? Closed really should mean closed under limits. Closed under limits. Closed equals closed under limits. And I mean closed in the sense of no escape, right? Like if you're in a closed jail cell, you cannot escape the jail cell. When I say a set is closed under limits, I mean if you take a sequence of points that is converging to something, then the something has to be in S. You cannot escape the set S by taking limits, would mean it's closed under limits, and that is really what a closed set is. So theorem 1.3.21 says a subset of S in a normed space or in a metric space more generally is closed if and only if every sequence of elements which is convergent has its limit in S. So you have your set over here, and you take some limit of points. So you have some sequence that is converging to something, I don't know, maybe it goes really wild and then it gets closer and closer to something. Well, that limiting point better be in the original set S. You cannot escape the set S. Notice that if you have a fuzzy boundary, this will not happen. So if you have a fuzzy boundary, like this is an open set, then you take some limit and you can get closer and closer to the edge, and the limit point will be right on the boundary, and then it is no longer in the sort of fuzzy set. So open sets, in an open set, you can sort of escape outside, but a closed set means you cannot escape. Let's prove theorem 1.3.21. So here is my proof. This is an if and only if, so we actually have to prove two things. I'm going to prove the first thing first, and I'm going to do it with an arrow, so it's a direction. If it's closed, then it contains its limits. So this is want to show. We want to show if S is closed, then let's say x1, x2, ... such that xn to x implies x is in S. So every time you have a convergent sequence with things in S, the limit is also in S. And the proof is a proof by contradiction. Okay, so every good proof by contradiction starts with the words suppose by contradiction. Otherwise, the reader will be confused. So suppose by contradiction, X is in S complement. That means in the set of things not in S. Then, what do we know about S? Well, S is closed, so S complement is open. So then, since S is closed, S complement is open. Okay, so what? So if S complement is open, what do we know? Well, we have a point in an open set. What's the only thing we can do? Therefore, there exists epsilon naught. Let's say there is some epsilon naught such that the ball centered at X of radius epsilon naught is contained in S complement. Again, we're using the property of open sets at the point X. I mean, it is true that it's a there exists statement, but I wouldn't write that there exists in this line in my proof. I would write there is some, because I want that specific value that works, right? So it's not that, there exists a generic epsilon. It's there's some specific value epsilon naught for this particular X, and that's what I'm going to use now. So it's a little bit of a proof writing technique here. Okay, so we have our epsilon naught, we have our X. Why is this a problem? Well, let's draw the picture of what's the situation is. Okay, so here's our set S, right? Here is our point X, which we assumed was in S complement, and we have drawn a little ball around it of radius epsilon. This is the ball of radius X, centered at X of radius epsilon naught. And now what is the problem is that we had all these points, x1 to xn, which were converging. Let's draw those in a different color. Here's x1, x2, x3, and so on. And they're converging to X. They have to get really close to X, but they always live in S. And how are they possibly going to get within epsilon naught of X without escaping S? This is the problem. The points in the sequence have to be in S, but they also have to be arbitrarily close. They have to be within epsilon naught of X, and they can't possibly do that. So how are we going to write this down? That's a nice picture idea. Let's see. So we have the ball. Okay. Let's apply the property of convergent sequences with epsilon naught. So since limit as n goes to infinity of xn equals X, therefore, let's say, therefore, there is some, let's call it n naught to go with our epsilon naught, such that xn minus x is less than epsilon naught for all n greater than n naught. Okay, so we've applied the property of limits converging with the epsilon naught we were given. That gave us an n naught. And now we have a contradiction. So what we're saying is that the points past xn, so xn naught onward, they are in this ball. But this ball, we said, is entirely in S complement. And that can't possibly be true. So this is a contradiction. Let's write it down. This is a contradiction. Since xn minus x is less than epsilon naught implies xn is in the ball of X with radius epsilon naught, which is a subset of S complement, as we proved before, but xn is in S by hypothesis. And this can't be true. It can't be in both S complement and in S. So this is contradiction. Contradiction. Let's write contradiction with a capital here. Some people do a little lightning bolt, which I like. Lightning bolt. Okay, we've reached a contradiction. So there's the proof by contradiction of why, if you have a closed set, it contains its limits. Oh, we only proved one way. We said if it's closed, then it contains its limits. So the other direction says if it contains its limits, then it's a closed set. And again, what do we know about closed sets? The only thing we know is that the complement is open. So we're going to say that if it contains its limits, then the complement must be open. And it's going to be, again, a proof by induction. It's going to be, again, a proof by contradiction, not by induction. And I'm going to leave it as a little exercise. So exercise, which is prove that if S contains its limits, then S complement is open. And the hint is, if you do it by contradiction, what would happen if it's not open? Well, then there'd be a point where there's no epsilon that works, and then you would make a sequence out of that. That's a really good exercise. Hint. If S complement is not open, what happens? Make a sequence. Okay, fantastic exercise. So this will be an exercise. Okay, that is open and closed. The next thing you can do with open and closed is talk about the closure. And the closure is the sort of, you take some set. So let me draw one of these like half open sets from before, and you close it by taking the intersection of all the closed sets that contain it. And when you do that, you sort of add in these points on the boundary. And so the closure will be the smallest closed set in some sense that contains the original set. And we denote this with CL of S, the closure of S. It's the intersection of all the closed sets containing S. And of course, it is a closed set itself because the intersection of any number of closed sets is always closed set. And here's another exercise from the textbook. This one, they don't even give the proof in the textbook. Prove that the closure is the same thing as adding in all the limits of X. Okay, and let me actually give a hint for this exercise. The way you prove this one is you prove containments both ways. So let's call this set limits. Let's call it L for limits. That's a good name. L. So L is the set of all the limits, and you're going to prove that L is a subset of the closure of S, and that the closure of S is a subset of L. And again, what's the definition of the closure? The closure is the intersection of all the closed sets E, where E is closed and S is contained in E. S is a subset of E. So if L is a subset of that, then it has to be a subset of every single such E. So that's what you prove to prove that one. And then the other way, you prove that if you're in every single such E, then you must be in L. So you prove inclusions both ways. That's my hint for this one. This is a nice, this is kind of an abstract-y proof where you're like, I don't actually know what these sets E are, the closed sets that make the closure, but it's just any closed set that contains S, and you use that property to your advantage. Okay, and what's the fun thing you can do with closure is you can talk about dense subsets. So a subset is called dense if its closure is the whole thing. The classic example of this is the rationals are dense in the reals. The rationals are dense in the reals. So what this means is if you think of a number line and you think of only the rational numbers, so that's the rational numbers are some kind of subset of the reals. Most numbers in some sense are not rational. Most numbers are irrational. But if you take just the rational numbers, there's sort of enough of them that you can construct any real number as a limit of rational numbers. And so if you take the closure of the rational numbers, the closure of Q, that's going to be chucking in all the possible limits of rational numbers, then you're going to get everything. So that will be all the real numbers. So this is called dense. Q is dense. It means when you take the closure in R, that means when you take the closure, you get back the whole thing. This is a very exciting thing. Here are some other examples. They wrote in the textbook, they said, the set of all polynomials on AB is dense in the continuous functions on AB. So what this means, if you look at all the possible polynomials, this is an infinite dimensional space. It seems very big, but in some sense, like a polynomial is not that nasty of a function. A polynomial is a nice function. And what this is saying is that if you take all the possible limits of polynomials, then you get all the possible continuous functions. So let's write that down another way. Let's say the polynomials, polys on AB. I think earlier in the textbook this was denoted by P of AB, is dense in C of AB. Okay, and this is, we're thinking of these spaces with the infinity norm, the max norm that we talked about before. And this statement, the polynomials are dense in C, it means if you take all the possible limits of polynomials, then you get all the possible continuous functions. Another way to say that is that this is true because every continuous function is a limit. A limit in what sense? A limit in the sense of the infinity norm, in the infinity norm sense. By the way, this little, I'm drawing the norm and I'm putting a dot because I'm just thinking about the norm, not a specific norm applied to a function, just the norm itself that tells us what the limits are. So every continuous function is a limit in the infinity norm of a sequence of polynomials. So this is a famous theorem that you may or may not have seen. This is called the Stone-Weierstrass theorem. This thing is the Stone-Weierstrass theorem. Has some very nice proofs that the polynomials are dense in all the possible continuous functions. You can approximate any continuous function by polynomials uniformly well. Okay, that's exactly what is written in example 1.3.24. So the Weierstrass theorem says that every continuous function can be uniformly approximated by polynomials. This can be expressed as follows. The closure of the set of polynomials is the whole space. So that's what they're saying over here. If the closure is the whole space, then the polynomials are dense in CAB. Here is another nice example. They're saying the set of all sequences of numbers which have only a finite number of non-zero terms is dense in lowercase LP. So lowercase LP, remember, is the set of sequences that are summable in the power p. So it's the set of sequences, so an going from 1 to infinity, such that the sum of an to the power p is finite. Okay? So these are infinite sequences, but they're sequences that have to go to 0 sort of fast enough that they are summable when you take them to the power p. If p equals 1, that's a good example to have in your head. That means the sequence is summable sequences. And what they're saying is, if you just look at sequences that have where this sum is a finite sum, so that is, some people call this space, they call it C0. It's the sequences n equals 1 to infinity, such that an is non-zero for only finitely many things. For only finitely many things. C0 is the sequences that have finitely many non-zero terms, and then there's 0 forevermore. Of course, C0 is a subset of LP, right? Because if you have finitely many non-zero terms, then of course the infinite sum is actually a finite sum and is finite. But what they're saying is if you do the closure of C0 in the P norm, you get LP. So the closure of C0 equals LP. Everything in LP is a limit of things that have finitely many non-zero terms. You can probably imagine what it should be, right? I'm going to approximate some sequence. I'm going to approximate it by something with finitely many non-zero terms. Which terms should I take? How big is the error? This kind of thing is how you would prove this kind of statement. So that is the statement they have written here in example 1.3.26. Okay, so that is open, closed, closure, some nice stuff. And we're thinking about them again in terms of functions and sequences and that kind of thing. The next topic and the last topic for this video is compactness. Compactness, very closely related to all these things. Definition 1.3.28 says a compact set is a set where every sequence contains a convergent subsequence. I will tell you, some people, for them, this is not the definition of a compact set. This is a sequentially compact set. So some people call this definition sequentially compact. In a metric space, which a normed space is a special type of metric space, sequentially compact is the same thing as compact. So the difference between compact and sequentially compact only comes up if you are doing some weird topology that is not a metric space. where like the open sets are given by something other than balls. So for us, sequentially compact and compact are the same. This is the textbook definition of a compact set. Other people's definition of a compact set is the open cover, finite subcover definition. That is the classical definition, but we're not going to do that one for now. So don't worry about that. If none of this made sense to you, just forget the last minute, and definition 1.3.28 is the definition of a compact set. You might remember in R, the Bolzano-Weierstrass theorem. So in R, the Bolzano-Weierstrass theorem, Bolzano-Weierstrass, one of my favorite theorems, says that every closed bounded set is compact. And that is what's written over here. Every closed bounded set is sequentially compact. I guess, okay, maybe the Bolzano-Weierstrass theorem actually says if it's bounded, then every sequence has a convergent subsequence. If it's also closed, then what it converges to has to be in the original set. So in any case, what we're getting at is the statement of 1.3.29. This is also called the Heine-Borel theorem. And again, the difference is normally the Heine-Borel theorem is stated in terms of open covers and finite subcovers, and the Bolzano-Weierstrass theorem is stated in terms of every sequence has a convergent subsequence, but they both are the same thing. In R, these compact sets are precisely the closed and bounded sets. So this is an important sort of thing that you've seen before, maybe in R. In infinite dimensions, unfortunately, compact is not exactly the same as closed and bounded. And what we're going to see is that compact implies closed and bounded, but the reverse is not true. So compact implies closed and bounded. That's coming up. That's going to be in just a minute. We're going to do that one. But the reverse is not true. So closed and bounded in general and bounded does not imply compact. This is in infinite dimensions. So in infinity dimensional spaces, in non-finite dimensional spaces, closed and bounded does not imply compact. In R and in like Rn, it does, but we are not in R or Rn. We're going to be working in these infinite dimensional spaces. Okay, what does closed and bounded actually mean? Well, closed we've talked about for a while now, but bounded is very simple. A space is called bounded if it fits inside one giant ball. For us in our normed spaces, this means there exists R such that the norm of X is less than R for all X in S, right? So you fit in the normed space if there's some R, so that bounds the norm of every single thing in the set you're talking about. Okay, so let's do the thing that I promised. We're going to prove that compact implies closed and bounded, and it really is two separate proofs. Compact implies closed, and compact implies bounded. Compact implies closed is quite easy given what we've already set up, so let's do that one. It's a good chance if you want to pause the video and try it yourself first. This one's not so hard, so let's imply closed first. And so what do we have? We have that S is compact. S is compact. And what does S being compact mean? Well, the only thing we know, definition 1.3.28, i.e. every sequence xn has a convergent subsequence xnk, which converges to x, which is in S. That was part of the definition. Okay, look, my body is in the way. So xn converges has a convergent subsequence whose limit belongs to S. So we know S is compact, which means every time we have a sequence, we can find a convergent subsequence, and that convergent subsequence has a limit X is in S. What do we want? We want to prove that S is closed. How do we prove that S is closed? Well, we could use the complement is open thing, but we have proven something else about closed sets, which is we're going to prove that every convergent sequence, so if the limit as n goes to infinity of xn equals y, then, so if you have some sequence which converges to y, then y is in S. That's what we're going to prove. I hope you can see how these two things are related. The thing we have says that, we've got these subsequences and they converge to something in S. And what we want to show is that the limit is in S. So how are we going to do it? Let's just write it out. So here's the proof. Let xn be some sequence, some arbitrary convergent sequence. Yeah, let's write it this way. To see S is closed, let xn be some arbitrary convergent sequence. The limit as n goes to infinity of xn equals y. Let y be its limit. And what we want to show is that y is an S. We want to show. Okay, so we want to show y is an S. That is what we want to do. That would prove it's closed by the theorem from earlier. Let's say this shows S is closed by that theorem. This shows S is closed by, okay, we can even scroll up and quote it. What theorem was that? It's closed if and only if. Here we go. Theorem 1.3.21. It's closed if and only if it contains its limits. This shows S is closed by theorem 1.2.21. I've already forgotten it. Okay, let's 1.3.21. Okay, amazing. Let's go fix the thing. Okay, lots of scrolling. Okay, so that's what we want. All right. Because S is compact, since S is compact, so we're given this xn. Because S is a compact set, what can we do with sequences? We can find a convergent subsequence. We can find convergent subsequence. Let's call it x and k, such that the limit as k goes to infinity of x and k equals x is in S. So this is all because of the definition of compact. All right. So we have this convergent sequence. We have a subsequence that's converging. Of course, the subsequence has to also converge to the thing that the original sequence does. Let's say since x and k is a subsequence of xn, and by, let's give this thing a name. Let's call this star. And by star, xn converges to y. So this is converging to y. Therefore, xnk also converges to y. So, if you have a limit of a sequence, every subsequence will have to converge to that thing. Of course, you could do this by epsilon n, right? If for every epsilon, there's an n beyond which xn is really close to y, then all the x and k's past that point will also be really close to y. So you could write this out. That could be like a little lemma if you want for this proof. I think as written, it is clear enough for what we're doing. Since x and k is a subsequence of xn by star, xn converges to y, therefore xn also converges to y. So limit as k goes to infinity of xnk equals y. And now by this thing, let's call this thing star star. Let's say by star star, limit as k goes to infinity of xnk equals x, y, which is the limit, which is equal to x. Therefore, x equals y are the same. So actually this thing called x and this thing called y are actually the same, and therefore y is in S, since x was in S, and they're the same thing. Okay, so there you go. So this is exactly the nice proof of the very simple idea going from what we have to what we want. We have that it's compact, so we have convergent subsequence that converge to things in the original set, and we want to prove that it's closed. We want to prove that any limit is in S. Okay, what about the second part? We proved that it's closed. Let's prove that it's bounded. Okay, and I have a little example. We'll come back to the example in a minute, but let's prove that compact implies bounded. Again, another good one to do as a sort of exercise if you want. Let's suppose by contradiction, actually, before we do this, let's write what we want. Have and want. We want to prove that it's bounded, so we want to find an R such that the norm of x is less than R for all x's in S. That's what bounded means. We got to find this R that works and kind of contains the whole set in that radius R. which means the norm will always be less than x. And what do we have? We have that's compact. So every sequence has a convergent subsequence, has a convergent subsequence. Okay, so how are we going to prove what we want using what we have? Well, I think what we're going to do is we're going to try to create some sequence and then feed that sequence into the have, and then we're going to get a convergent subsequence. And that is going to be the thing we can do. How can we create such a sequence? Well, what if, if it wasn't bounded, then no matter what R we picked, we would always be able to find something outside of it. And that would make a sequence for us. So by looking at bigger and bigger balls, eventually either they cover everything or we can find a point outside of it. And that's how we're going to build the sequence. So the thing I just said is the sort of idea. Here is the actual proof. The proof is proof by contradiction. Suppose by contradiction that it is not bounded, that S is not bounded. So what does not bounded mean? Bounded means there is some R. Not bounded means no matter what R you pick, it will not work. So i.e. For all R greater than 0, there exists X in S such that absolute value of X is bigger than R. That's the countering the statement of boundedness. Okay, very nice. So this works for all R. So in particular, we can plug in R equals 1, 2, 3, 4. So in particular, taking R equals 1, then R equals 2, etc. We find x1 such that the norm of x1 is bigger than 1, x2, these are all things in S, such that the norm of x2 is bigger than 2. And I can do a ... xn in S such that the norm of xn is bigger than n. Okay, of course, you could have written just this line for any n. You could have done this, but by writing the 1, 2, I think it's a nice way to lead the reader into what we're doing here. So by feeding in bigger and bigger radiuses, if it's not bounded, we can always find something outside of it. Okay, so we have this sequence of xn's. Now we feed the sequence of the xn's into what we have, which is the compactness. So since S is compact, we can find a convergent subsequence. So this sequence of xn's, has a convergent subsequence. So x and k converging to something. K goes to infinity. Let's call the limit x. Okay. Now here's the thing. When you have a limit, the norms will also converge. I think that was an exercise from before. By properties of convergence. This could, again, you could prove this as a separate lemma. It's actually, I think, almost trivial using like the triangle inequality. But okay, let's just say by properties of convergence. So if the limit of the x and k is x, the limit of the norms is also respected. So the norm of the x and k equals the norm of x, right? So because of the limit, the norms have to converge. On the other hand, but the norm of x and k is greater than nk by construction. Of x n, right? So the sequence was constructed. You could give this a star. You could say by star, the norm is bigger than nk. It is going off to infinity. That is exactly how we constructed the thing. So if it's always larger than nk, then the limit, so the limit as k goes to infinity of the norm of x nk actually equals infinity, contradicting the limit from before. So let's give that a name, contradicting star. Okay, there we go. And that's a very nice little proof. Okay. Okay, that proves that if you are compact, then you are bounded. And together with the thing we did before, we have finished off example 1.3.31, that if you are compact, you must be closed and bounded. Now, the reverse is not true in infinite dimensional spaces, and that is what this example is saying. Let me give you some more maybe easy examples first. So in infinite dimensional spaces, closed and bounded does not imply compact. Okay, and the simplest possible one I think of, and I always remember, is if you look at sequences, so look at infinite sequences, say with the soup norm or whatever norm you want. So these are sequences of the form an, n going from 1 to infinity. Those are the elements of the space. Let's do little l infinity. So this is the maximum of n going from 1 to infinity. I guess it's the soup, not the maximum, because infinite things sometimes don't have maximums. The soup of the an is less than infinity. So bounded sequences. This thing already has this closed and bounded, but no compactness thing. And the simplest example is look at the sequence EI. Look at the sequence of vectors. So here's the thing, right? The vectors themselves are sequences. So this is a sequence of sequences. Like, you really have to have your head screwed on straight, where you're like, okay, a vector is a sequence. Now I'm looking at a sequence of vectors. What sequence am I looking at? The sequence of vectors E sub n. And E sub n is the particular sequence that has zeros up until the nth slot. And then it has zeros forevermore after that. And so, E1 is 1 and then all zeros. E2 is 0, 1 and then all zeros. Zeros after. E3 is 0, 0, 1 and then all zeros. And these are the usual coordinate vectors in like ordinary linear algebra class, like the vector of x, the x direction, the y direction, the z direction. It's just that when you're in this infinite space, it goes on forever and ever. So En just goes on forever and ever. You can always have an nth slot, and there is no like last coordinate, right? That can go up as far as you want. So this is En, and the norm of En is always 1, right? The maximum value is always 1. It's all zeros except for 1, 1. And here's the thing. There is no sequence that this converges to. The limit as n goes to infinity of En does not exist in L infinity. The reason it doesn't exist is the thing that it would be converging to, sort of, and the thing that it converges to point-wise is the vector of all zeros. So every single coordinate is getting closer and closer to 0, but you will never get close to something in norm because the norm is always 1. So what would you get close to that is all zeros but norm 1? It just doesn't work. So the limit does not exist. You can't get close to any particular thing. And again, this is a version of that sliding spike example that we saw, right? It's a spike sort of in the nth component of size 1, and that spike kind of slides out to infinity and ruins the limit. So this is, I think, the most basic example. You should really learn this one of closed and bounded does not imply compact. If you look at the set of ENs, they are bounded because they're always norm 1. To make it closed, you just need to have some closed thing that contains all of these. So for example, the closed unit ball would work. So the ball of radius 0 would be centered around the 0 vector with 1. All the ENs, the sequence of ENs that I just described, is in that ball. And that ball is therefore not compact because this sequence of the ENs has no convergent subsequence. Yeah, so not only does the limit not exist, but any subsequence would not exist for the same reason. It would have a 1 sort of going off to infinity, and that subsequence would also not converge. So this is a really good example. What does the textbook say? The textbook also wrote an example. They wrote the example of the functions t to the n. That's a nice example. So here's example number 2. This example is more complicated. This is the example in the space of continuous functions on 0, 1. And they look at the sequence of functions of powers. So the first function they look at, f1, is a line. Then the second function they look at, f2, is a quadratic. f2 of t equals t squared. f1 of t equals t. f3 of t equals t cubed, and so on. So these are powers. And as you take the powers, it is going to 0 pointwise, except for exactly at x equals 1. So the limit Fn of t equals t to the n, the limit as n goes to infinity of Fn of t, this is the pointwise limit, this thing, it is, okay, it's either the limit as n goes to infinity of the sequence of 1 to the n, which is just 1, and that's if t equals 1. So if t equals 1, it's always 1, it's just converging to 1. And if t is not 1, then you have the limit as t to the n, and t is strictly less than 1, and that limit is 0. So it's 0 if t equals 0. So you can see kind of from the little cartoon, the values here at any particular thing are going all the way down to 0. So it's converging pointwise to a function that is 1 when t equals 1 and 0 if t equals 0. That's sort of what you would like to say it converges to. But this limit is not a continuous function. And so the fn's, the limit of the fn's does not exist in the space of continuous functions. Okay. And any subsequence of it will have the same property. Any subsequence will also have these convergences of converging to 1 at t equals 1 and 0 at t equals 0. So any subsequence will also not have a limit in this continuous space. And that is why, this sequence is showing that the C01 has sequences that have no convergent subsequence, and therefore it's not compact. I guess the last thing you should check, and I guess maybe I was kind of doing this without saying, the norm of the fn's is always 1. So all of these fn's live in the closed unit ball of radius 1. So once again, just like in the sequence space, the closed unit ball has sequences with no convergent subsequence. It's not compact. So the conclusion, therefore, the closed unit ball around the 0 vector with radius 1 is not compact. Okay, and this is the total opposite of what we're used to in linear algebra class, where by the Heine-Borel theorem, or the Bolzano-Weierstrass stress theorem if you want, closed bounded sets always have convergent subsequences. Here, closed bounded sets don't have convergent subsequences. Okay, that's enough for today. That's where we're going to stop. Open, closed, closure, compact, that kind of thing.